In this screencast, we'll talk about how to use Android content providers and Minmax game state utility repositories. And as usual, we'll start with a few demos that will demonstrate the software that we will develop in this screencast. So the first one is the Tic-Tac-Toe content provider. So when you start this application, essentially it registers the content provider by first creating a database from a text file, a database of boards and move utilities for each of the players, X and 0. So it's about 180 kilobytes, and it's going to take a couple of minutes, but the database is created as in an asynchronous task. So, and then the second component is the Tic-Tac-Toe client application that actually uses the content provider to play the game of Tic-Tac-Toe. It essentially demonstrates that the AI of a Minmax game can reside in a content provider. It doesn't have to reside in an application, so that other applications, Minmax applications that maybe want to put Tic-Tac-Toe, the game of Tic-Tac-Toe, in their suite of games, then they can use the same content provider to implement their intelligence. So, all right, let's do a little bit of Minmax game theory. So, Minmax games, generally speaking, are so called because they're two players. The first one is called Max, and the second player is called Min. Max typically starts, and Min moves, and then second, and then they take turns. The objective of the Max player is to maximize the gain or utility, and the objective of the Min player is to minimize utilities. So here's Max, red states, and then Min, blue states, and green states are the final states. So this particular tree encodes a two-move game, right? First Max makes a move, Max 1 and Max 2, and then Min makes a move depending on the move of Max 1. Okay, so another very important component of the Minmax game is the utility function, right? And also the fact that there's a finite number of finite set of moves available to each player. The number of moves is not infinite. So the utility function basically takes a state, for example, a board, if it is a board game like chess or tic-tac-toe, and then it can outputs a number, right? A real number, but typically it's an integer, a negative or a non-negative integer. So for example, in game of tic-tac-toe, if we take a look at this board, then the utility function, if applied to the board state, may, for example, return, and it does in our application discussed below, 1 if the board state is a win for X, 0. Yeah, let me put this curly brace. 0 if it's a draw, and then -1 if it's a loss for X or a win for 0. All right, so and that's so these components are sufficient to compute the utilities of the final states, compute the trees, and then we can percolate the utilities upward. So for example, if we can know that these are 4, 10, 5, 2, 15 are utilities of the final states, final board states, then since Min chooses, right, from the final states, then we're going to select the move Min 1, right, from the left child of the root of the tree. Right, so because that's the minimal utility, and the job of the minimal player is to minimize utilities, right? So to minimize the gain of the player Max. So hence the utility of this board is 4, right? The right child, the left child of the root of the tree, right? The root of the tree is that red node with Max. Okay, so once we've computed this utility, the utility of this inner node, we can compute the utility of this, the right child of the root of the tree. And the utility of this is 2, and so min should choose min 4 in this state because that's what leads to the minimal utility. Once we have the utilities of the two blue inner nodes, we can compute the utility of the root node, which is 4 because it's Max's turn to play, and Max always chooses 4. So Max always chooses maximum utility, so and 4 is greater than 2. So Max should choose Max 1. That's the move, right? Available to the Max player. So this example gives a generic min-max algorithm. So essentially, we are given a start state. Say, for example, the game of Tic-Tac-Toe, start state, and then we are given a finite set of moves available to each player. Or actions, sometimes they're called, because it doesn't have to be a game, it can be some sort of economic situation, because min-max games are frequently used to simulate various economic conditions. So a finite set of moves and a utility function. Right. So once we have those three pieces, we can essentially compute a min-max game state utility tree. Right, so we can compute the game tree. So start with the root that we know that's Max's turn to move, and then we apply all of the possible moves that Max can make, and then it's Min's turn to move, and we can apply from each of the states all of the possible moves that Min player can do, and so we can compute this entire tree. So and then we can apply the utility function to the leaves and percolate the utilities upward all the way to the root, as we did in the example. Right, so if it's min always chooses the minimum, and Max always chooses the maximum. Now the question becomes, well, is it always possible to compute such a tree? And the answer is no. Like, for example, for the game of Tic-Tac-Toe, yes, it is. The game of Tic-Tac-Toe results, if I remember correctly, the mathematical analysis of this game basically allows for a total of 237,168 games. So it's a large number, but for modern SQLite databases, it's not that big a number. So we can actually compute the entire tree in a couple of minutes. However, if it is chess, then it's obviously out of the question. So what do we do? Well, we can compute partial trees. So for example, every 200 plies, right? So we can compute a tree of 200 moves from a given state of the move, then watch out which move is made by the opponent, and then recompute the tree, or just look it up if we care to save the results of the partial computation. But regardless, we will have some form of tree. So let's once we have the in order to compute the tree, we need to decide on the board state encoding, and in the game of Tic-Tac-Toe we will be using strings to encode board states. So for example, so let's say if we have an empty board, then we will encode the fact that a specific cell is empty with a question mark character. Right, so like the empty board can be encoded as the string of 9 question marks. So the first 3 question marks are the first row, the second 3 question marks are the second row, and then finally the last 3 or the third 3 question marks are the third row. So for example, this state can be encoded as the first row is X, then we have 2 question marks, then the second row is question mark, then 0, and then another question mark, and the third row is just 3 question marks, right? Because there is no move. There's okay, nobody has moved there. So this is the first row, this is the second row, and this is the third row. Row 1, row 2, row 3. Okay. So this is how we can encode. Now let's talk about the source code, and I will not go over the source code. The links to the source code GitHub projects will be available in the description of this screencast. So here's the generic structure of the source code. So we have a tic-tac-toe game tree generator. And it's a Java 6 application, and essentially this Java 6 application generates a text file where every state is encoded in terms of the state of the board, the player whose turn it is to make a move, and then a utility a number for each move. Right, so it can also be a serialized object. Doesn't have to be a text file. All right. So then once this is done, and this is done not on Android, it's done somewhere else. That text file is generated. Then we have a content provider. And the content provider takes this text file and content provider creator application that runs only once. And the purpose of that application is essentially to register a specific content provider on the Android ecosystem, and then to create an SQLite database from the text file for that game. Right, registers CP on the Android ecosystem, and then creates an SQLite database on top of which the content provider sits. So once that database has been created on the Android ecosystem, various applications can use that content provider to play that game. Right, so one could be, for example, if we're in a game of tic-tac-toe, as we are in this project. So we can create a dedicated client application, or perhaps someone else wants to do some game theory research. So that individual can also use that content provider, and then another programmer wants to develop a suite of tic-tac-toe. A suite of applications, so that content provider can also be used. So here's the GitHub repository and for this project. The links will be provided again in the description of this guide. This is the Tic-Tac-Toe Minmax utility tree generator. It's a Java app. It's not an Android app. If you run it, essentially it creates that a game state utility tree and translates it into a text file. And then that text file, we take that text file and place it into the content provider application. This is the content Tic-Tac-Toe content provider creator application in the assets directory. And when that content provider runs, it registers the content provider on the Android ecosystem, and then uses that text file to create an SQLite database. So it's going to take on my emulator, it does take a couple of minutes, because it has to create over I don't know 5,000 insert 5,000 SQLite records. So because the entire tree is computed. And finally, Tic-Tac-Toe Touch Play 0002 is the client application that uses the content provider, finds it via the content resolver, and uses it to play the game of tic-tac-toe.